Okay, welcome back, everybody. Okay, so today we're going to go a little bit deeper into linear differential equations. Just a review of what we did last time. So we went over some of the basic kind of methods in calculus, how to do the derivative, the chain rule, things like that. We looked at the simplest linear ODE, x dot equals lambda x, where x is just a single scalar number. Okay. We started thinking a little bit about what the exponential function really means. So E is, of course, Euler's number. Anything that has Euler's name on it is really, really important. And this time we're going to start looking at more general ways of solving these differential equations using Taylor series. So this is going to be one of the most general techniques in the class. You can solve almost any differential equation just by assuming a Taylor series and plugging it in. Okay? So you can always find the lecture notes online. This is the overview of topics today. So like I said, we're going to go over Taylor series and how to solve linear systems. We're going to go into what a Taylor series actually means and do some MATLAB examples, so plotting some Taylor series approximations. And then we're going to start looking at second order systems like the linear harmonic oscillator if we have time. Okay? Okay, so when I say second order or higher order, that really means the order of the highest derivative of our variable. So x dot equals lambda x is first order because I'm taking one derivative. X double dot plus x equals 0 is second order because I'm taking two derivatives. And in general, I could have like a 10th or a 9th or an 11th order differential equation if I had 9 or 10 or 11 derivatives. Okay? Okay. Good. Can everyone see the board on the screens? Yep. Okay, good. Okay, so we're going to start with Taylor series. All right, just a quick show of hands. How many of you remember somewhat what Taylor series are? How many of you would like a bit of a refresher on Taylor series? Okay, good. So this is going to be a lecture where we really go deep into Taylor series. We'll come back to it a couple times, but we're going to really start using it pretty heavily in the future lectures. Okay, so we have our first order linear differential equation, x dot equals ax. X is just a number, it's not a vector or anything. And we know from last time that the solution is x at time t is equal to e to the constant a times time times my initial condition x at time 0. Okay, we got this last time. And we started thinking about what does this e to the at function mean, this exponential function? So we're going to derive this another way using the Taylor series. Okay, so let's use Taylor series. And what that means is that we're going to assume that our function x of time has a certain functional form, and then we're going to solve for the coefficients of that function. Okay? So x of t, we're going to say that this equals some constant term plus another constant times time plus a second constant times time squared, third constant c3 times time cubed, and so on and so forth forever. So I'm going to say plus higher order terms. Okay, HOT just means higher order terms. I could also say order delta t to the fourth, because there's terms of t to the fourth. Sorry, just order t to the fourth, t to the fifth, to the sixth, and so on and so forth. Okay? Okay, so we're going to assume that we can write our function x like this, and then we're going to essentially take its derivative, plug it into this equation, and solve for these coefficients c. How many of you have done this before in differential equations? How many of you have not done this before? Okay, so this is a pretty powerful technique. Sorry? Okay. Okay, so let's get going. So the time derivative of x, we literally just take the time derivative of every single one of these terms in order. Okay, so what's the derivative of a constant? 0. Okay, derivative of c1 times t? Just C1. Okay, so C1 plus 2 times C2 time plus 3 times C3 time squared plus 4 times C4 time cubed plus ... Okay, good. So now we're going to multiply this term by A and plug it into the equation. Ooh, it's a little loud. I'm going to close the door. Okay, so A times x dot is just AC1 plus 2AC2t plus 3AC3t squared plus 4AC4t cubed plus a bunch more terms like that, okay, forever and ever and ever. And now I'm supposed to take x of t. Okay, I did something wrong. What did I do wrong? Okay, I really should do a times x, not a times x dot, right? Okay, let's try this one more time. Okay, a times x is just ac naught plus ac1t plus ac2t squared plus ac3t cubed plus ... That looks better. Okay, and now I want x dot to equal ax. And I'm just going to do it term by term. Okay, so I'm going to take all of the different powers of t, and I'm going to make their coefficients match forever up until infinity. Okay? So the constants term, if I have the t to the 0 term, I have a c1 here, and that has to equal a times c naught here. Okay, so c1 equals a times c naught. Fine. Okay, in the t's terms, I'm matching 2c2, and that has to equal a times c1. Okay, this is starting to look like a pattern, right? So I have a 4-year-old son, and everything is a pattern now, he thinks. Okay, so t squared, we have 3c3 equals a times c2. And so on. So let's just write the last one. So I'm guessing it's 4 times c4 equals a times c3, right? Good. Okay. Okay, so what's the next step in this progression? What do we do next? Sorry, is there any other information I have about this differential equation? We know the initial conditions, right? So we know that x at time 0 is just x naught. Okay, so I can call this, x sub 0 if I want. So if I plug in t equals 0 in my Taylor expansion for x, I get that c0 has to equal x0. Okay? So this is equal, so c0 equals x0, and that means that c1 is a times x0, and 2 times c2 is a times c1, but c1 equals a times x0. So I have a squared over 2 x0 equals c2. Does everyone see how I did that? Right, so I plugged in a times x0 here. I got a squared x0, and I divide by 2. A squared x0 divided by 2. Okay, c3 is the same thing. I plug in this for c2. I get an a cubed x0 divided by 2 divided by 3. So divided by 3 factorial. C4 is a to the 4th x0 divided by 4 factorial, and all the way down to Cn is going to equal a to the n x0 over n factorial. Okay? And so now that we have all of these terms in terms of the initial condition, the constant of the differential equation A, we can plug these into our Taylor series and get an expression for x. Okay? So x of t was equal to c naught plus c1 times t. So that's x naught a times t plus c2 times t squared over 2 factorial. Yeah, plus c2 times t squared is a squared over 2 t squared times x naught plus c3 times t cubed is a cubed over 3 factorial t cubed x naught. And I can pull the x naught out of all of these and get 1 plus at plus at squared over 2 factorial plus at cubed over 3 factorial plus dot 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 times x naught. Did I mess something up? I'm sorry? Like here, for example? Okay, so the reason there's a factorial, I'm some
previous terms have been.
Yeah, so the previous term C2 has a 1/2 in it, and then I divide by another 3. So I have a 2 times 3 in the denominator. Then in this term here, C3 has a 2 times 3 in the denominator, and then I divide by 4. So I get a 4 factorial in C4. And this.
So it's just that you wanted to express all the terms in terms of x.
Right, yeah, so we're getting everything in terms of x naught. Okay, so essentially we haven't assumed anything about the solution except that we can write our solution as some expansion in powers of t. And then we solve for what the coefficients of that expansion have to be. And what we get out is the exponential function. So this is e to the at times x naught. And in general, this is a pretty common way of doing things. So if there's a differential equation that comes up a lot of times in physics, what I might do is plug in a Taylor series expansion, solve for the coefficients that that expansion has to have to satisfy the equation. And if I end up using that function all the time, I'm going to give it a name. I'm going to say, I define this function to be e to the at. Right? You can think of sines and cosines and e to the at's and cosh's as sinches. Those are just special functions that have Taylor series expansions that come up a lot in physics. Okay? Bessel's functions, Airy's functions, they can all be derived from key critical differential equations. Okay, any questions about this Taylor series example? Any at all? Nope. Okay, good. So let's do a little review on what Taylor series really mean, just get some examples. So we're going to use Taylor series over and over and over again. And so I really want us to just be very, very comfortable with these. So for example, I might, in the future, have a vector of states x. So I might have a bunch of numbers that are changing in time. And they might be related by some big matrix A. And the matrix exponential, e to the matrix A times time, times a vector of initial conditions, will be the general solution of that system of equations. So most of you have probably seen this before. And the way that we interpret this matrix exponential is by using the Taylor series expansion of e to the at and plugging in matrices for A. Okay? So using the Taylor series is going to be really, really important. So why don't we just go into a little bit more depth about what the Taylor series means. Okay. So I think the Taylor series is probably the high point of calculus, at least the calculus series that we all take, like 1, 2, and 3. Taylor series is the foundation for all of the numerical approximations we'll do in this class. When we do numerical integration or differentiation of data, when we take a differential equation and try to integrate a trajectory through it, for example, if we're going to predict where a spacecraft or a satellite's going to go, or if a comet's going to hit Earth, right? We're going to have approximations to the solution of that equation, and the quality of our approximation is going to depend on the Taylor series terms. Okay? So the Taylor series. Okay, a function can be expanded in a Taylor series if it's sufficiently smooth. So smooth means it doesn't have, terrible kinks or discontinuities. It means what we think it means by smooth. So a function f of x plus delta x can be Taylor expanded at a point x, and this is if f is sufficiently smooth at x. So there's a bunch of conditions that I'm going to kind of gloss over. Most of the functions we care about have Taylor series expansions. And we write it like this. So f of x plus delta x probably is equal to f of x plus df dx evaluated at my base point x times delta x plus d squared f dx squared, the second derivative of my function evaluated at x times delta x squared plus, and I can just keep going all day long, dx cubed evaluated at x times delta x cubed plus dot 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 plus the nth derivative of f with respect to x at x delta x to the n plus dot 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 dot. Okay, this goes on forever and ever and ever. Okay, so there's two key parts of this Taylor series expansion. What are the two key parts of this? What are the two variables here? X and delta x. Okay, so the way I think about this is I have some function f of a variable x. I pretty much always draw the same function. Don't know why. Always have. And the idea is, if I know my function f at some base point x, and I also know its derivative, and maybe its curvature, and its third and fourth and fifth and higher order derivatives, then I can get a really good approximation for this function in some neighborhood around x, some x plus or minus delta x. Okay? So for example, if I just know the first derivative, df dx evaluated at x, I know the slope of this line, then I can approximate f of x plus delta x by just taking f of x and adding where that line would take me. Okay, that's my first order Taylor series expansion. A second order Taylor series expansion will bring me down on this parabola and get me much, much closer to the solution. Okay? So this is an extremely useful form for approximating smooth functions in a neighborhood of a point if I know something about the smoothness at that point. Smoothness just means that the derivatives exist. Okay? You'll hear me say that a lot. Okay, questions about the Taylor series expansion? Yeah.
So when you go from like something, question caught up. So when you go to like a discrete representation of a smooth function, how do you define smoothness?
So I guess you would assume that the function that discrete representation was derived from is smooth and has derivatives. So for example, if I want to solve a fluids equation with the Navier-Stokes equation, I'm going to do it on a discrete domain of a bunch of gridded points and gridded in time. But my equations, the Navier-Stokes equations, are twice continuously differentiable in space and once continuously differentiable in time. So I just know that my solution has to have that amount of smoothness. Okay, so I have to have first and second derivatives in x. Okay, so I'm going to write this just another way because I really want us to be able to use the Taylor series very, very naturally. So we'll do another quick example, or rather another representation, and then we'll do a MATLAB example. Okay, so another way we can write this is, let's say we have a function f of x expanded about a base point called A. So in the board on the left, our base point is x, and we assume that delta x is a small distance from x. So another way to say this is that f of x is going to be expanded about some point A. And I can say, well, f of x is going to equal f of A plus df dx at A times x minus A. Now I hope this is small, right? This is like my delta x. This is playing the same role as delta x. Plus d squared f dx squared at A x minus A squared plus so on and so forth. This is just another way of writing it if I don't want to use x's and delta x's. And you can convince yourself that this is exactly the same as what I wrote on the left board. If you let x minus A equal delta x. Okay. So let's do an example in MATLAB. Okay, so we're going to do our first example. How many of you really know like the Taylor series of most functions by heart? Like if I asked you what the Taylor series of sine of x is, how many could just tell me right now? No? Okay, this is going to be super important stuff. This is one of those things you should know. Really, really important. Okay, so and I'll tell you why it's important in a little bit. Okay, so our first example is going to be f of x equals sine of x. Okay, so how do I... Okay, we're going to do f of x equals sine of x, and we're going to expand about a point A equals 0. So this has a special name. This is called a Maclaurin series. Okay. And so we can essentially just apply this formula. We know that sine is super duper smooth, right? I can take the derivative of sine all day long, and I get nice clean functions that can be evaluated on the whole number line. So we're going to just do this exact same procedure. Okay? So this is equal to f of 0. What's f? F is just sine. So it's equal to sine of 0. That's this term. Plus the derivative of sine at 0. What's the derivative of sine? Cosine. So cosine of 0 times x plus, okay, what's the second derivative of sine? Minus sine, right? Derivative of cos is minus sine. Minus sine of 0 times x squared over 2 factorial. Did I mess up? Feel like there's supposed to be some factorials here. Okay, you guys need to catch me on this. If I miss factorials, the whole framework collapses. Okay, so all of these terms have a really important factorial term that keeps this series convergent for most functions. Super important to have these factorials. 1 over 2 factorial, 1 over 3 factorial, and so on and so forth. Okay? Okay, the third term is the third derivative of f with respect to x. So what's the derivative of minus sine? Minus cosine. Minus cos of 0 x cubed over 3 factorial. Plus sine of 0 x to the 4th over 4 factorial minus, no, plus cos 0 x to the 5th over 5 factorial. And we can just keep going because there's a pattern. Okay? So sine of 0 is always 0. Cos of 0 is always 1. And so all of the terms with sine 0 go away. And I'm only left with the cos 0 terms. So I have x plus x cubed over 3 factorial, minus x cubed plus, good, I'm keeping everyone awake today because I have not had my coffee, plus x to the 5th over 5 factorial. What do you think the next term is going to be? Minus x to the 7th over 7 factorial plus dot, 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 and we can just go on and on forever and ever. Okay? So this is the Taylor series expansion of sine of x. It's kind of funny, right? We can write sine of x in terms of a bunch of odd polynomials. But you need all of them. Okay? Any idea what f of x equals cos x equals? It's all of the even terms that we forgot. So this is kind of an exercise you can do. This should be 1, I think, minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial and dot, 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 dot. Okay, questions about the Taylor series on these specific examples? Right, all we needed to know was f and its derivatives, all of its derivatives, at the point x equals 0, and we can get this entire Taylor series expansion. Okay, who would like to see this actually coded up in MATLAB to see kind of how good the approximation really is? Okay, let's try it. Okay, so you can find the MATLAB code online. It's also in the notes. So let's try this. Okay, good. Okay, so first things first, we're just going to plot our sine wave. So I clear all, close all, and CLC. I think that means it clears the command window. So I'm going to create a vector x from minus 10 in increments of 0.01 to 10. Okay, this is a big vector from minus 10 to 10 in increments of 0.01. It's about 2,000 points. Okay, and the first thing I'm going to do is just plot my sine function. Okay, so I'm going to plot x by y in black, and I want it to be big, so I'm going to make it line width 2. Let's call this test Taylor. Okay, there's my sine wave. Okay, so now we're going to try our different Taylor series approximations to this. Okay, I'm going to make an axis which goes from minus 10 to 10 in x and minus 10 to 10 in y. And I'm going to turn a grid on, and I'm going to hold on. So hold on allows me to plot other things on top of this. So I'm going to go a little bit fast on the MATLAB. I'm going to assume most of you have seen some MATLAB before, but I really want to build up your ability to make nice figures in MATLAB. Okay? Okay, so now what we're going to do is plot the first order Taylor series approximation. First order Taylor expansion. Okay? So how many of you have seen the polyval and polyfit commands? Only a few of you. How many haven't? It's okay if you haven't. Okay. So polyval and polyfit is just a really, really nice, cute little MATLAB code that allows you to define the coefficients of a polynomial and then evaluate that polynomial on a vector of x values. Okay, so that's what I'm just going to use for shorthand. If you want to know more about it, you can type doc polyval or doc polyfit, and you can get the whole documentation of what it's doing. We're actually going to write our own polyval and polyfit in a couple of weeks. Okay, so our first order Taylor series approximation was just x. So it's a polynomial with leading coefficient 1 and constant coefficient 0. So this is just x plus 0. Okay? That's the coefficients of my x polynomial. And I'm going to say that my Taylor series of first order is equal to polyval. I'm going to evaluate my polynomial, p, at my vector x. Okay, so I've defined a polynomial p. It's just x. And I'm going to evaluate that polynomial at my grid of data points, negative 10 to 10. And now I can plot x by my first order Taylor series expansion in blue in a smaller line width. Okay, that's my first order Taylor series approximation. Kind of cool, right? And so you notice that in a vicinity of the origin, x equals 0, it's actually not too bad of an approximation, right? It's got, in fact, the error will be proportional to delta x cubed, because those are the terms that I'm leaving out. Right? I'm getting all the delta x terms. I'm leaving out all the delta x cubed and fifth and seventh. So if delta x is small, my error is going to be small. Okay, now let's do a third order Taylor expansion. So this is on the homework. I just posted the homework this morning. I wrote it just before coming to class. And there's going to be an example like this where you're going to kind of compute a Taylor series and then plot it. Okay, so this should be easy. P equals, what's our third order Taylor series approximation? Minus 1 over 3 factorial x cubed plus x. Okay, so what is that? Minus 1 over factorial 3, 0, 1, 0. Right, so this is my delta x cubed term. I have 0 delta x squared terms, and I have 1 delta x, and then 0 constants. That's my Taylor series expansion up to order 3. And I can say that yt3 equals polyval p evaluated at x. So I'm going to evaluate that new polynomial at my points x. And I'm going to plot x with my third order Taylor series expansion, let's say in red. Okay, and I'm just going to keep going and going. So I'm going to do a fifth order. So to do that, I need to add minus 1 over factorial 5, I think. Not minus, plus. Thank you very much. And this should be a green, so I'm just going to make this match my script. Okay, and finally, the seventh, I'm going to have a minus 1 over factorial 7, 0, yt7, and let's make that magenta. And I should probably put a legend up, right? Because I've added a lot of plots now. Okay, so my first function is sine of x, followed by first order, third order, fifth order, and seventh order. Good. That's how you do a legend. Okay. So that's my Taylor series approximation for increasing orders for sine of x. Okay, and it's kind of interesting, right? I have, I start with the blue curve, then I get my red curve, the cubic term, then the green term, which is fifth order, and finally the magenta curve, which is seventh order. So what we're finding is that to capture these switchbacks in the sine function, I need higher and higher order even polynomials. But the convergence is really terrible. If I want to go 5 or 6 periods out, then I'm going to need a ton of polynomial orders to really capture that. Okay? So this is just a kind of quick example of how to do Taylor series, how to visualize them, and how to interpret them. Okay? Any questions about the MATLAB code or the physical interpretation? Yeah?
Not about the MATLAB code, though.
Okay, sure.
So the size of the neighborhood in which you're solving depends on the order of the Taylor expansion that you're taking, or vice versa?
So there's a few ways of thinking about this. If you have higher and higher and higher order Taylor series expansions and your function is sufficiently smooth, then your radius where your function is accurate gets bigger and bigger. That's one way to think about it. That really only works for very smooth functions, because there could be some point at which no Taylor series approximation will work, okay, if there's some really big discontinuity. Another way of thinking about this is if I always have a really small delta x, so I'm always in a very small neighborhood of x equals 0, then my Taylor series expansion gets more and more and more accurate. Okay, so the error for this magenta curve has order delta x to the 9th. Because those are the terms that I'm leaving out, or the delta x to the 9th terms. So if delta x is 0.1, my error is like 10 to the minus 9. It's 1 billionth. Really, really small. Okay, that's another way of thinking about it. And if I zoom in here, let's just try to zoom in. This might be a little hard to zoom in enough. Well, they all look way too good. Okay. So these orders are polynomial. So I would have to actually subtract each of these values from my true sine x and plot the error on a log plot to see the error decreasing for higher order. Okay? That's something you can do, right? You can take the black curve and subtract all of these approximations from it, and then plot the log of the absolute value to see the error in log space. Okay, good. Okay, what do you see in the back on the screens? Do you see the board? Or me? Me? Okay, good. Okay, so a final example, just to really drive this home. So I'm going to poll you a lot this class just to figure out what you do and don't know. Complex analysis. How many have some experience with complex functions? Like if I wanted to plug complex numbers into sine of x or e to the ix, how many have not seen this or would like a big refresher? Okay, good. A little bit more than half of you. Okay, so Taylor series are also really, really nice because they generalize to complex valued functions really, really well. Okay? So one of the examples that's going to be super important, we're going to find examples of functions where we need complex valued solutions. So differential equations that have complex valued solutions. So I want us to get pretty comfortable with complex numbers. And so in particular, we're going to start by saying, what is e? Well, first of all, what's the Taylor series for e to the x? We just wrote this down. It's 1 plus x plus x squared over 2 factorial, x cubed over 3 factorial, x fourth over 4 factorial, x fifth over 5 factorial. This is one of the functions that is actually worth knowing by heart. It's so powerful and versatile. You're going to use e to the x is the basis for the solution to all linear differential equations. Every single one of them that you can possibly write down, the solution is related to e to the x. Higher order systems of equations, harmonic oscillator equations. It's worth remembering this function. Okay. Now, what if I plug in e to the complex number I times x? Okay, remember I just equals the square root of -1. Okay, someone was clever one day and started taking the square roots of all of the numbers and realized that when they tried to take the square root of -1, there was no number that 1 squared equals -1, so they invented the number I, so that when you square it, it's -1. And algebra was born. So if I take e to the ix, how do I evaluate this complex valued function now? Okay, sounds like you remember the answer. I could plug in ix every time I see an x here. Very generic way of doing things. The Taylor series is one of the most generic ways of representing a function. So this is equal to 1 plus ix plus ix squared over 2 factorial plus ix cubed over 3 factorial, ix to the fourth over 4 factorial plus, I don't really need to keep writing this, dot, dot, dot. Okay? And what I'm going to do is I'm just going to expand all of these powers of I times x. So I'm going to get 1 plus ix plus, what's I squared? -1, so that's minus x squared over 2 factorial. What's I squared times I? Just minus I. So minus I times x cubed over 3 factorial. Now, I to the fourth is I squared squared. It's -1 squared is +1. And now we start it all over again. So now we have a plus I x to the fifth over 5 factorial, and so on and so forth. Okay? Now, if we really want to, we should represent this as a real part plus an imaginary part. And so I'm going to collect all of the things that don't have I, which happen to be these even powers, x to the 0, x2, x to the 4th, x to the 6th. Right? That's looking familiar. And I'm going to collect all of the odd terms that have an I. And I'm going to write this as, 1 minus x squared over 2 factorial. That's my cosine. Cosine of x plus I times sine of x. Okay? So e to the ix is equal to cosine of x plus I times sine of x. Again, this is called Euler's formula. And what did I say about things that are named after Euler? Super important. Okay, this is one of the most important equations in all of mathematical physics. Really simple. Just says that I can take my exponential function and I can solve that exponential function for complex variables, e to the ix, and I get cosine of x plus I times sine of x. Okay, any questions about complex numbers, Euler's formula? I mean, if this is new, like having questions is totally fine. Even if it's not new, it's totally fine. Okay? Does this make sense? Yeah? Okay. Okay, so the next thing we're going to do, I'm just going to get this started in this lecture, and we're going to continue it in the next lecture, is we're going to start thinking about more general differential equations. So far we've been dealing with the simplest equations we can think of, which are just x dot equals a times x or lambda times x, linear first order equations. And very quickly in the next 2 lectures, we're going to generalize this to all linear differential equations with higher order derivatives. Okay? So we're going to look now at second order ODEs. And these are going to look like x double dot plus x equals 0, for example. Okay? I could write other expressions that have, I could write x double dot plus x equals 0. So what's the defining characteristic of a second order ODE? Has a second derivative. It doesn't have any third or fourth or fifth derivatives, but it definitely has to have a second derivative. That it's a second order system. Okay? So what's a really good example of a second order ODE? This is like the equation we keep coming back to over and over again in physics. Spring and mass. A spring and a mass, right? Okay, so I have some mass m, and I have a spring k. And I have some displacement that is the displacement from rest x, okay? So assume that if I just let my spring, equilibrate so this thing's not moving and there's no forces, that's 0. And x is any displacement in addition to that rest displacement. So if I take my mass and I pull it some amount x and I let it go, what's going to happen? It's going to oscillate, right? It's going to go back and forth. So this is nice because we have some physical intuition for what the system is going to do. And we can write down the equations really, really easily. So Newton's second says F equals ma. Okay, so what's the force on this mass? Okay, something like k, is it minus kx? Yeah, let's say minus kx. So it pulls it back if x is positive, and if x is negative, it also pulls it back. Okay, so minus k times x equals mass times x double dot. right? Acceleration is just the second derivative of position with respect to time. And so we get our equation x double dot equals minus k over mx. Okay, this is our second order harmonic oscillator. Okay, so we're going to start solving systems like this. We're also going to go to generic higher order systems, like x triple dot plus 2x double dot plus x equals 0, things like that. Or maybe I have a fifth or a sixth derivative. So we're going to go up to arbitrarily high order differential equations in the next 2 lectures. And we're going to use complex valued exponential functions to do it. Sorry, so we're going to use e to the lambda. So here's what I want you to do. I didn't get quite as far as I wanted to today. So there's 3 methods of solving this system, and I want you to explore each of them before next lecture, or at least the first 2. So method 1 is guess a solution. Right? We just discussed if I pull this mass off of equilibrium and let it go, it oscillates back and forth. So pick a function that you know oscillates and try to solve this differential equation. Method 2 is also to guess. But now instead of just guessing a solution, let's try e to the lambda t. Let's try some solution e to the lambda t, and let's plug it into this equation and solve for what lambda has to be. Okay? You're going to find out that you get a complex valued exponential that's going to give you cosines and sines. Okay? So that's what we're going to do next lecture, and then we're going to generalize to higher order ordinary differential equations. And at that point, we're going to go into systems of multivariate ordinary differential equations. Okay, so homework 1 is posted online. You can find it on the course website. There's now a link to the course website on the Canvas page where the videos are recorded, so you can find, hopefully, everything pretty easily. The first homework is due this Friday at 4 o'clock. You can email it to me and the TAs, or you can hand it in class. This shouldn't be a very long assignment. Okay, this is mostly review. Okay, I'll see you all on Wednesday.